Calorimetry.
Calorimetry.
Not color.
It's calor, isn't it?
Calor.
Mr. Sam? Not calor is not the same thing as color.
No, so it's like calories.
So this comes from the word calories.
Yeah. So that's how we're measuring heat. That's a unit of heat.
So metry stands for like a meter.
Measure, yeah.
Meter or measure.
So we're going to measure heat.
Calories or measure heat.
Okay.
Yeah. So how do you measure heat is the topic of today's podcast.
With a heatmometer.
With a heatmometer. But the problem with heat is it has to be measured indirectly.
Ah.
And so we're going to teach you guys the process, or really the scientific method that you use to measure heat.
Okay.
So that's what we're going to talk about. Okay? Well, before we start, Mr. Sams, we should talk about thermochemical equations, just to kind of do a little review here for our brains.
Yep.
There's something called heat of combustion. What the heck is combustion?
Combustion is when something reacts with oxygen. Usually we have hydrocarbons that react with oxygen.
A Cha or a Cho reaction.
Yep, and we make CO2 and H2O as our products.
All right. So the heat of combustion is the heat change for a combustion reaction. Okay. And so actually what people usually don't care that they make carbon dioxide and water. They actually care they also produce some variety of energy.
Right.
And that energy, by the way, one thing true about combustion reactions is that all the time they're exothermic, which means their energy is released. Or we would say delta H is always negative for combustion reactions.
Yeah.
Okay, well, let's talk about, so just a little review probably. If a reaction is endothermic here, well, the value of delta H goes on the
left side of the equation.
Left side, the reactant side. So it always goes on the reactant side. So if I've got A plus B makes C, the energy would go on the left side for endothermic reactions. The reverse is true for exothermic reactions. So if I've got A plus B turns into C, you get energy produced, and so it's on the right side or the product side of a chemical reaction.
Stuff we talked about before.
But just good review.
Yep.
It's very important. All right, calorimetry. We're just talking about calorimetry, which we introduced at the beginning. It is an accurate and precise measurement of heat change for a chemical and physical process. So we want to measure heat.
Right. Can't do that directly, though. We have to measure what heat does.
It's always done indirectly, pardon me. And so here is kind of a way to look at this whole process right here. Here we have a container down here. Okay, and the reaction is taking place in the yellow container, and then energy, in this case, is being released. It's been an exothermic reaction, and it's heating up the surroundings, which is blue.
Right, and those surroundings are probably going to be water in the devices that we use to measure this. So, yeah, basically we're going to measure temperature change in water. If the temperature of the water goes up, it's an exothermic reaction. If the temperature of the water goes down, it's an endothermic reaction.
Perfect. That's exactly right. All right, let's talk about this. A calorimeter is a device that measures the calories.
Yeah.
It's insulated, so it's an insulated device, and it can measure the absorption or the release of the heat in a chemical or physical change. Basically, our calorimeters that we've been playing with are those, 5-cent
styrofoam cups.
Styrofoam cups.
Yep.
But you can buy the $500 variety or $5,000 variety, and you get a very, very specific one that's a insulated container. The reaction takes place here, and they measure it. They've got thermometers in and out, and this blue substance right here is just water, most likely.
Now, in here we've got a little chamber that the reaction takes place in. For our purposes in our class, our reactions are all going to take place in water, but they're going to be dissolved in water. That's not going to be in a little chamber in the water.
And as we've already said, usually water is the chemical that captures the heat, and you use the equation Q equals MC delta T, which we talked about in a previous podcast. Okay. All right. Here's our cheap calorimeter that we get to use. All right. Now, we need to define one term, by the way, and we've probably used this, but it's probably important to just kind of review it for it. The term enthalpy we have been referring to as delta H, which is the change in H, or heat. Okay, and the fancy term is it's called delta
enthalpy.
H. Well, like I said, it's just delta H, or K, and the equation, which we've already talked about, is Q equals MC delta T. Sort of. So here's actually, how do you calculate delta H? Well, the first thing I want you to understand is the units for delta H is kilojoules divided by moles. So to do this, what you're going to do is you're going to have to get the numbers from two different places. To find the number for kilojoules, you'll use the equation Q equals MC delta T, where Q is your kilojoules, if you will. You'll actually get joules.
Joules, right. Q gives you joules. You're going to have to turn it into kilojoules by dividing by 1,000.
You must have it in kilojoules, not the joules. Okay. And the moles is the moles of, actually, I want you to write this down. It'll be the moles of the limiting reactant. And usually we're going to mass something. And if you know the mass, you can quickly convert it to the moles using a conversion of grams to moles. Yeah, molar mass. All right.
Then you just take the kilojoules divided by the moles, and you have delta H.
That is exactly correct. All right. So I think we should actually do an experiment.
Let's
Mr.
do
Sam.
it.
So let's do an experiment where we actually, we actually do this.
Yeah.
Okay. All right. Today I want to talk about how we can find the heat of reaction of magnesium plus hydrochloric acid. So hydrochloric acid right here, I have 100 milliliters of hydrochloric acid. Hydrochloric acid is close enough to the density of water. I can assume that 100 milliliters is 100 grams. So I'm going to pour that into my cheap calorimeter. Okay, I'm going to measure the initial temperature with my trusty thermometer. And the original temperature is, looks like 19 and some change. It's going down, 19.21. All right, 19.1 degrees Celsius. So I'm going to write that down. I got 19.1 degrees Celsius. Now I have my magnesium. I need to know its mass. So I'm going to stick it on the scale. So as I stick it on the scale, its weight is, mass actually, is 0.67 grams. Now I'm going to put this in my cool data table that I have in just a minute, and I'm going to just add this to this, and we're going to see what happens. Now an important thing is if the temperature goes up, it's going to be exothermic. It's going to release energy. If the temperature goes down, it is going to be endothermic, or delta H will be positive. So we're going to see what happens. We're at our 19.1 degrees Celsius. I stick it in there, and if you look here, it's fizzing. Mr. Sams will zoom in on that. All right. It's fizzing very rapidly. The temperature is increasing quite rapidly. It's producing hydrogen gas, by the way, which is quite cool. Now, and it's gassing out Mr. Bergman because it stinks. 37. We're at 19. This is very exothermic. 41 degrees. And we're waiting for it to completely react, which means essentially we're waiting to stop fizzing. So we're trying to get that to stop fizzing right there. 46 degrees. It's quite warm now. Whew! I would not stick my finger in there now. The fizzing is just... I wouldn't
stick my finger in there to begin
with. Yeah, because it's hydrochloric acid. Yeah. So, looks like we are done now. It's at 48.7 degrees Celsius.
Okay.
I think we should go back and do the calculations and find what is the value of delta H for this reaction.
All right, so here's all the data that you collected there, Mr. Bergman.
Yep, this is what I got.
Right, we've got the mass of our magnesium there, the mass of the HCl that we use, and our initial and final temperatures. So if we want to determine delta H for this reaction, first we need to find Q using MC delta T.
Right.
And then we're going to divide it by the moles of our limiting reactant. Now, which one of those is our limiting reactant, and how do you know?
Well, as I watched the experiment occur, I saw the magnesium completely be consumed.
So if all the magnesium got used up, then that's our limiting reactant. So we're going to take the delta H is going to be our kilojoules of the reaction, divided by the moles of magnesium in this case.
So here's our reaction for all this. Right. We need to find the kilojoules and we need to find the moles. So to find the kilojoules, like we said, we're going to use the equation Q equals MC delta T. And for the moles, we're going to find the moles of magnesium because it was the one we ran out of. So let's do the MC delta T first.
Okay.
So Q would be equal to the mass. Now
right.
The mass was 100
grams of HCl.
Now, why HCl? Now, why not the magnesium, Mr. Sams?
Well, the HCl is mostly water, and again, we're measuring the temperature change of the water that is that all these things are dissolved in.
Yeah, so it's the HCl that's doing most of the temperature changing. Right. If you really wanted to be specific,
it's the
you
water
probably
in
could
the
say
HCl.
100.67, but it's close enough that it doesn't matter. Now, our change in temperature here is
48.7 minus 19.1.
So let's do that. 48.7 minus 19.1.
That's 29.6.
29.6. Save that on your calculator, Mr. Sams. So actually, my C, now you say, well, what's the C of hydrochloric acid? Since it's mainly water, it'll be 4.18 joules per gram degree Celsius times my temperature, which was
29.6.
29.6 degrees Celsius. That gives me a grand total of 12,373 joules. Now I'm going to quickly convert that to kilojoules because it makes life easier.
Yeah,
that'll be 12.4 kilojoules. Now let me find the moles of the magnesium. Now I had how many grams?
0.67 grams.
Grams of magnesium. I know there's 24.3 grams in 1 mole. I got that from the periodic table. So I looked on my periodic table, found that that's the answer, and I get what?
0.0276.
0.0276 moles. That goes up right there.
Okay.
Now,
then we just divide.
so my delta H will be 12.4 kilojoules divided by 0.0276 moles. And I get like 400 something, Mr. Sampson, in it.
You get 449.
449 kilojoules per mole. Now, the interesting thing is, Mr. Sampson, that is the wrong answer.
What?
Yeah, well, your calculator just gave you that, but that's still wrong because we've done one thing, one thing we've not done is we need to think about the sign of delta H.
Oh, yeah.
Because delta H needs to either be positive or negative.
Right. Well, the temperature of the water went up.
Yep, so the temperature went up.
So that's an exothermic reaction.
An exothermic always get a negative answer.
Okay.
So delta H is equal to negative 449 kilojoules per mole.
Right.
And actually, I think the real answer is like negative 460. So
Yeah, I think
this
it's pretty
is
close.
Pretty close to the real with a
styrofoam
2-cent
cup.
Styrofoam cup.
That's right. And our amazingness.
All right, let's do a second example, Mr.
All right.
Sams. Okay. So here we have a different one. It's really a very similar type problem. We have ammonium chloride dissolves. So ammonium chloride is NH4Cl. It's not that important you write this reaction, but we'll just go ahead and do it. That's a solid, and when it dissolves, it turns into ammonium ions, and we would put AQ because it's dissolving into water, which is an aqueous solution, and chloride ions, AQ. Okay, what do we know?
We have 2.25 grams of ammonium chloride, so we could probably get moles from that.
2.25 grams of that, yeah.
Okay, we've got 100 grams of water and the temperature change. So we could use the mass of the water.
So delta H is kilojoules divided by moles. So let's do the MC delta T thing here.
Okay.
So this is MC delta T, which is, now here we'll say, should we say 102, Mr. Sams?
I'd say 100.
100 grams times, it's still in water, so we can use the 4.18 joules per gram degrees Celsius. Now, I don't have to subtract the beginning and final
No,
temperature.
it tells us what the change is.
It
That's
drops.
the delta T.
That's delta T. So we don't have to like subtract. They give it to us. And what do we get there, Mr. Sams?
It's 4305.
4305 joules.
4.3 kilojoules if you want.
Yeah, well, let's do that at the end then. And
Okay.
the moles, I'll have 2.25 grams. Now, this is the ammonium chloride because that's the substance that dissolved, so it's the limiting reactant. I can say grams in 1 mole. I think it's like 8476. What is it?
I have absolutely no idea. I'm putting in my calculator right now.
All right, so we're trying to find the molar mass of NH4Cl.
It is 53.5.
53.5, and then when we divide this, we get
0.0421.
and that's moles. So to find delta H, it'll be the kilojoules, and the kilojoules will be 4.3 kilojoules. I divided by 1,000, divided by 0.0421 moles, and we get
102.
102
kilojoules
per mole. Now that one will be positive, Mr.
Right,
Sams.
because it's endothermic.
Because it's endothermic, because it dropped the temperature 10.3 degrees.
All right.
Okay, so it's just like the other problem, except kind of doing an endothermic example. And the last example is the trickiest one. Okay, we have a reaction. Shouldn't there be another product here?
Nope.
Okay, an extra plus.
Heat.
Oh yeah, plus energy. So we have a reaction with the delta H, and so I'm going to write, because since it's negative, I'm going to write 851.5 kilojoules. Now, why did I not put a negative sign there, Mr. Sams?
Because you wrote it as a product, and as a product, it's implied that it's exothermic and therefore negative.
Okay, so that's the question. Now here, the chemicals are quickly dropped into 1,000 grams of water. If 23.5 grams of iron is produced in the reaction, how much will it raise the temperature of the water?
Okay.
So we want to see how much the temperature goes
Right, so we're
up.
solving for delta T.
So delta T is the question mark, right?
Right.
All right, so let's see if we can do that.
Okay.
So let's go to another screen here. Here's our reaction, and we had
23.5? Yes, 23.5.
23.5 grams of iron, so I have 23.5 grams of this.
Okay.
And I want to convert this to energy.
Right.
And then I'm going to essentially solve for Q. That'll be Q,
That
and
is
equals
Q.
MC delta T, and I will then plug that in and solve for delta T.
Okay.
So this is like kind of a combination of the stoichiometry problem we did a while back. So I have 23.5 grams of iron over 1. Now the first thing I must do is convert grams of iron to moles of iron. They are 55.8?
Yep.
55.8 grams of iron. I found that on the periodic table in 1 mole of iron. The grams of iron cancel. Now I'm going to use the mole to kilojoule ratio. I'll say 2 moles of iron, now I get that from the 2 right here in the coefficient, is 851.5 kilojoules. My moles of iron cancel, and I get kilojoules.
179.
179 kilojoules. That's sort of equal to Q. The problem is that's in kilojoules.
Yeah, we need it in joules.
Yeah, we need it in joules. So I'm going to say 179,000 joules, that's my Q, right, is equal to MC delta T. My mass, if you recall,
1,000 grams.
was 1,000 grams. The C is still that 4.18 joules per gram degrees Celsius times delta T. Now we divide both sides by
1,000 and 4.18.
1,000 and 4.18. And we get an answer.
We get 42.8.
So it's 42.8 degrees Celsius.
Right, now
did it
that's...
ask for the final temperature, or did it ask
it
for
said
the...
ask for the temperature change. How much did it go up? How much will it raise the temperature?
42.8 degrees.
Yep.
Now, interesting question. Sometimes they might ask you the question, what is the final temperature?
Right.
So let's say let's say that the initial temperature, TI, was 20 degrees Celsius. Since this is exothermic, energy is on the product side, we would then add the 42.8, that's a 4, degrees Celsius, and you get 62.8 degrees Celsius.
Okay.
Or if it had been endothermic, you would have subtracted it,
Yep.
which would have been a little tricky here because it had gone below the freezing point. We'll deal with that actually in a later podcast.
Okay.
I think that's it. So, ladies and gentlemen, that high math, isn't it? A lot of math on this one. But, well, hey, science, chemistry, math,
They all go together.
they go together. We'll see you in class or
Bye.
on the